All right, today we are working on a new chapter, and it is lesson 6.1, and we are working with adding and subtracting polynomials. The next couple lessons we'll get into then multiplication and division. So we're talking about naming polynomials and adding, subtracting them. So the first thing we want to talk about is, in general, a monomial is a number or a product of numbers and variables with whole number exponents. So a monomial is one term. That's when we have one term. And it's created by having a product of numbers and variables, and you can only have whole number exponents, no negatives, fractions, or decimals. The more general term is called a polynomial. Much like a polygon is any closed-sided figure, a polynomial is a monomial or sum or difference of monomials. Each monomial and a polynomial is considered a term, and they are separated by addition and subtraction. All right, if I have a binomial, that means I have two terms, much like a bicycle. So that comes from having two terms. And a trinomial comes when I have three terms. So we need to know these names. If I have one term, I specifically call it a monomial. If I have two terms, I'm going to name it a binomial. Three terms is a trinomial. Anything beyond, anything four terms or beyond, we name a polynomial. Four terms or beyond, we name it a polynomial. All right, so let's talk about what the rules of polynomials are. Polynomials may have no variables in the denominator. That's one of the rules, okay? They may have no variables in the exponents. No roots, square root, cube root, no roots, no absolute values of variables, and all variables have to have whole number exponents. So some ideas that are polynomials: 3x to the fourth. That is a monomial, and so that falls under the category of polynomial, and it follows all of the rules. All right, something like 2z to the 12th plus 9z to the third. That is also a polynomial. Specifically, it has two terms. We would call it a binomial. I can have a fraction as long as my variable has a whole number exponent. So I can have half of a to the 7th. I can have a decimal as a number, 0.15 x to the 101st. Again, as long as I have a whole number exponent. I can also have something like 3t squared minus t to the third. Again, that is another binomial, and it follows all the rules. Now let's break some of the rules to show what's not a polynomial. 3 to the x. That breaks the rule of having a variable exponent. No variables in denominators or exponents. All right, if I have something like 8 over 5y to the second, that breaks the rule of having a variable in the denominator. If my variable is in the denominator, that is equal to having 8 over 5 with y to the negative second. A negative exponent moves your variable to the denominator, and so if I have y to the negative second, that is the same as having y to the second in the denominator, and that breaks the rule of having a variable in the denominator or not having a whole number exponent, as negative 2 is an integer, not a whole number. All right, other rule breakers. If I have 2b to the third minus 6b, that is okay. But the minute I have variables in absolute value signs, that is no longer a polynomial. So I may not have any absolute values of variables. All right, I have this 1/2, but the issue is I have the square root of x. So no roots. Because having this, and we're going to learn this later in the year, is the same as having 1/2 x to the 1/2. A root is the same as a fractional exponent. And so it breaks that rule of whole number exponents, it breaks the rules of roots. All right, another idea, if I have m to the 0.75 minus m. That 0.75 breaks the rule because it's not a whole number exponent. All right. The degree of a monomial, as in one term, the degree of a monomial is the sum of the exponents of the variables. So the degree of a monomial is the sum of the exponents of the variables. I'm going to stress that there. So our next set of examples are all monomials. One term put together with multiplication. So I have a coefficient, I have a variable with a degree times another variable. Now what I want to do is identify just the degree of each monomial. So this is x to the fourth. There's only one variable, so the degree is simply 4. I'm going to go ahead and go vertically down here. So when I have this, the 4 is my constant. I'm not worried about that. I'm looking for the sum of the exponents of the variables. A has a degree of 2, but don't forget, B has a degree of 1 that's known. So the degree of this term is 3. Part E, 5x to the third, y the second, the degree is 5. It comes from the degrees of the variables. I'm going to jump over here and work my way up. A to the sixth, B to the first, C to the second. So the degree should be 9. So if it helps you to put that little 1 there, do so you don't forget it. X to the third, y to the fourth, z to the first. Again, I'm finding the sum of the exponents of the variables. And so this would be a degree of 8. And this is the one that gets everyone. I have the number 12 here. And the degree of 12 is actually 0. Now I get it. 12 to the first is 12. But it says the degree of a monomial is the sum of the exponents of the variables. And so there's no variable here. So if I take this and rewrite it as 12x to the 0, now we're talking. And anything to the power 0 is 1, getting me back to my 12. So there truly is a degree of 0 because I can write x to the 0. Anything to the power of 0 is 1. Now the next thing you want to remember is that this is called a constant. That's going to come back up. All of these have variables on it, and they have a coefficient, but because they have variables, this number can change. This will always be a 12. It's considered a constant. All right, so we're going to dig a little deeper into degrees, but instead of just looking at a monomial, we're going to talk about the degree of a polynomial. And the degree of a polynomial, so when I have more than one term, is the term with the greatest degree. The term with the greatest degree. That determines our degree of our polynomial. So let me give you an example here. If I have something like 5x squared y to the third minus 4xy to the second plus 6y minus 2. I have 4 terms here. 1, 2, 3, 4. So this would be considered a polynomial. The degree of the first term is 5, 2 and 3. The degree of the second term is 3, 1 and 2. The degree of the third term is 1, and the degree of this constant is 0. And so when I look at each monomial, this overall would have a degree of 5. So each monomial, I add up the degrees of the variable. But when I'm trying to find the degree of a polynomial, I look at each monomial individually, and this has the highest degree, so this is the degree of the overall polynomial. I do not add up each monomial. So you add up the degrees in each monomial, and then you compare the monomials, and this one's the biggest, so it would be a degree of 5. Okay, now, standard form is how we always want to write our numbers. So standard form is when the terms are in descending order, from highest to lowest degree. In standard form, the degree of the first term indicates the degree of the polynomial. Okay, so the degree of the first term is basically telling us this is the degree of the polynomial. So this is in standard form, and so that's the degree, 5. And the leading coefficient is the coefficient of the first term. Coefficient of the first term. Now, we have to remember, coefficient is the number out front. So the degree is 5, but the leading coefficient is also 5 here. This has a coefficient of -4, a coefficient of 6, and truly this is a constant, but with x to the 0, it's a coefficient of -2. All right, so these are the names that we need to know. If I have degree 0, I call that a constant. So if you want an example, something like -9. I have a number, no variable, that is considered a constant. If you want to look at it, it'd be the same as having -9 x to the 0, which is -9 times 1. That's why it's a degree of 0, and we call that a constant because it's never going to change. There's no variable. If I have a degree of 1, we know we call that linear because x to the first forms a line. So if I have something simple like 3x minus 4, and I think about putting a y equals in front of this, 3x to the first makes a line. So that's how I'm going to remember that it's linear, degree of 1, something we've worked with. All right, a degree of 2, we know it's called a quadratic. What makes something a quadratic is that x squared. So as long as I have an x squared, I know I have a quadratic. Now I can build this up. It can be something like 2x squared minus 4x plus 3. Power of 2, power of 1, power of 0, standard form. So since the highest degree is 2, this would be a quadratic, and if you want, trinomial. All right, degree of 3, something we should know, we call that cubic. So another term we're familiar with. Degree of 3, as long as I have x to the third, and that's my highest degree, then I would have a cubic polynomial, in this case a cubic monomial. If we build on that, maybe we have x to the third plus 4x squared minus 5x. Again, it is cubic because the highest degree is 3. I could even tack on here a minus 1. All right, 4, quartic, so help yourself remember, that'd be like quarters, quartic, 4 quarters, quartic. And as long as I have the highest degree of 4, so let's say I have 3x to the 4th minus 8. That is considered a quartic binomial. And the idea of having a degree 5 is called quintic. Okay, I think one of the harder ones for people to remember, unless they're familiar with the term. So quintic is 5. And again, I'll make a big one here. 7x to the 5th. As long as that is my highest degree, I can call this a quintic monomial. If I add on to it, I'll have 7x to the 5th plus x to the 4th minus x to the 3rd plus 3x squared plus 2x minus 1. So I have a quintic polynomial, and it's in descending order: 4, 5, 4, 3, 2, 1, and a degree of 0. All right, so it's really important that we know our name by degree. Over here, this was the name by number of terms. Type of polynomial it was, so nomial is number of terms, and here are the terms for degrees. So we're going to go ahead and we're going to use these. So we have a set of directions here we want to follow carefully. It says to rewrite each polynomial in standard form. Identify the leading coefficient, we're going to call that the LC. Identify the degree number, we'll call that D. Number of terms, I will call T. And then we are going to name the polynomial with 2 names, number of terms and degree. So I want to start out here by finding the highest degree, which has 4x to the 3rd. And then my next degree would be 2, I don't have it. Then my next degree is 1. So plus 2x and then minus my constant. All right, so I have it in standard form. The leading coefficient is the number in front of the highest degree, so it's 4. The degree of the overall term or problem here is 3, because that is the highest degree. And the number of terms is also 3. So how do I name that? Well, by degree, it is called cubic. And by number of terms, it is a trinomial. So it is a cubic trinomial. All right, again, I want to look for the highest degree, which happens to be x to the 5th. The next highest degree is x to the 3rd. So positive 7x to the 3rd minus 11x minus 2. So we're skipping a couple of degrees, but we go in order. Leading coefficient is in front of the x to the 5th, which is a 1. How many, what's my highest degree? It is 5. And how many terms do I have? 4. So when we go to name this, it is a 5th degree, so we call it a quintic. And since it has more than 3 terms, we call it a general polynomial. All right. Negative 5x squared is your highest degree, positive 4x, and ends with a positive 3. Leading coefficient is negative 5. Degree is 2. Number of terms is 3. So we name this by the degree. That is a quadratic trinomial. All right, last one, same thing. I want to scan through the problem. The highest degree is 4, so 8x to the 4th, a positive 3x squared, and a negative 4. Once I look at that, I determine the leading coefficient is 8, the degree is 4, and the number of terms, 3. So by degree of 4, I name it a quartic. 3 terms would be a trinomial. In our next set of examples, we're going to add and subtract polynomials. It says in the directions to add or subtract, write your answer in standard form, and we're going to take it one step further. We're going to go ahead and we're going to name it. Name the polynomial for practice. Okay, first thing I want to do is I do want to follow my order of operations. I want to see, before I add, is there anything to distribute? Nothing in the parentheses to do, nothing to distribute. Again, nothing in the parentheses to do. If you take a minute and look, this is a quadratic trinomial, and this is a cubic polynomial. But notice that this is not in standard form. So I want to be really careful about how I sift through this. I want to look at everything and say, what's the highest degree? And that's x to the 3rd. And there is no other x to the 3rd. So I'm going to start with 14x to the 3rd. My next degree should be 2. I have a 3x squared and a positive 1x squared. So I get a positive 4x squared. Next thing I'm looking for is a degree of 1. And I have it. I have a plus 1x and I have a minus 1x. And those end up canceling out. So I have 0 x's. And then I'm going to look for my constant, which is a plus 7 and a plus 2. And I get to end with a positive 9. So again, I want to scan through and find all my powers of 3, all my powers of 2, powers of 1, and then powers of 0. Now that I have that, I can see that I have a highest degree of 3, so that's called a cubic. I have 3 terms, so a cubic trinomial. All right, I'm going to scan this problem again and look. I have a cubic trinomial, and I have a cubic polynomial. I have nothing to do inside. I have nothing to distribute. So I really don't need the parentheses here. They're just there to show the grouping. And now I'm going to add like terms. So highest degree is 3. So I'm starting with this 2x to the 3rd and a 1x to the 3rd. So 3x to the 3rd. Degree of 3, degree of 2, that's all I have, is a positive 5x squared. I build it with the addition subtraction signs from the positive and negative outcomes. Then I'm going to go to x to the 1st, and I have a negative 1x and a positive 7x, which gives me positive 6x, and then my constant, positive 9, and a positive 4, so plus 13. All right, highest degree again is 3, and this would be a cubic, 4 terms, polynomial. All right, if I take a minute and I scan the next problem, the big difference here is I'm not adding, I am subtracting. And so one of the mistakes that is easily made is to forget about that subtraction symbol. So I'm going to suggest that we change it. We multiply everything in the second set by negative 1, which is in turn changing all the signs. If I choose not to change that sign, I'm likely to miss something. I'm likely to take 12 and a negative 2 and say I get 10. But it really should have been a 12 minus a negative 2. So I can do this without changing the signs, but I think it helps us to make less mistakes. So I'm going to distribute this and make it addition of the opposite. So a negative 15, a negative 3, and this becomes a positive 2. Every sign gets changed. Now I'm just going to go through and I'm going back to adding. So I have one less thing to think about. A little extra prep at the beginning helps me make less mistakes later. 5x to the 3rd is my highest degree. And then I have a 6x squared and a negative 15x squared, which gives me a negative 9x squared. All right, so degree of 3, degree of 2, now I need my degree of 1, and I only have it here. So if I didn't change that sign, I probably would have written a 3x instead of realizing it was minus 3x. And last are my constants, plus 12, and again, I changed it so I caught that it was minus and negative. A positive 2 becomes 14. Same title, cubic polynomial. So it's really important to take a minute and look at what we're doing, because in the next lesson we're going to be multiplying these, and that's something that's really easy to mix up. So I want to look and say that I'm subtracting. I'm going to change my signs. Addition of the opposite, so that becomes a negative 3x squared, a negative 2x, a positive 5. Highest degree is 2, so I have like terms here. I get a negative 4x squared. Then I get just a negative 2x on its own, and then my constants of 6. This would be a degree of 2, so we would call it a quadratic, 3 terms, trinomial. All right, the last example on this side, we see that we have 3 pieces. So I have a cubic trinomial minus a cubic trinomial plus a quadratic binomial. Nothing changes here, but that minus sign affects everything in this set. It does not change anything in the last set. So I'm going to go ahead and distribute that to everything in the middle set. And that is it. It does not extend out. And so I'm going to go through all 3 now. I don't need these parentheses anymore. And I'm going to go, the highest degree is x to the 3rd. So I have a 1x to the 3rd, or just x to the 3rd left. And then I need a power of 2. So there's no powers of 2. So you want to make sure you're not just pairing numbers up. This is my only power of 2. So plus 2x squared. Then I want my degree of 1. So negative 2x and a positive 3x is 1x. Oops, and then I subtract 1x. So I end up with 0 x's. When I go to add my constants, I have a 1 and a negative 1. So this is it. This is my answer. The x to the 1st and the constant canceled out. This gives me a cubic binomial. Our last set of examples are an application problem. So we are looking at cardiac output of the amount of blood pumped through the heart. The output is measured by a technique called dye dilution. A doctor injects dye into a vein near the heart and measures the amount of dye in the arteries over time. So each person, each individual patient will have a different formula based on their age, their ethnicity, and their gender. So the cardiac output of a particular patient can be approximated by this function. So f of t, and we have 0.0056 t the 3rd minus 0.22 t the 2nd plus 2.33 t. T represents the time, and that is in seconds after the injection. Now, the time goes from 0 seconds to 23. That is all the time we're using. After 23 seconds, the test is over. The dilution of the dye is no longer valid for our test. And the F of t represents the concentration of dye in milligrams per liter. Okay? So it says here to evaluate F of t, the function over time, for t equals 0 and t equals 3. Remember, t stands for the number of seconds. So in 0 seconds, we have not started this test. So when I take and find the function of 0, and I put 0 in as my input, I put 0 in, and 0 here, and a 0 here, I get out 0. So f of 0 is 0. Then when I come back and find out what happens to this dye in 3 seconds. So I would take my calculator and I would type in my number times 3 to the 3rd minus this times 3 to the 2nd plus this times 3. Once I take the time and I put that input into my calculator, I get 5.1612. Now we have a follow-up question. This is a word problem, so we need to know the meaning of this. So what do the values represent from part A? Well, the first value stands for the idea that in 0 seconds, there is 0 milligrams per liter of dye in the arteries. In 3 seconds, there is 5.1612 milligrams per liter of dye in the arteries. Now they're measuring this in a specific area. So you would have to be a doctor or someone who's been trained to read this and compare. Are these numbers good? Are they too high or too low? And at that, then what medical attention does the patient need? So we just know that the time was spent was 0 seconds and how many milligrams per liter of dye is there. All right, so we have another problem. We have another patient. You can see that this formula is very different for this patient. And when we're looking at it, we are evaluating it for t equals 4 and t equals 17. So we're going to do the same idea. We're going to take f of 4, and we would take that 4, and everywhere we see a t, we're going to replace the 4 in our calculators. Once we do that, we would get 3.8393. We're going to come back at f of 17, and we're going to come back and put a 17 in here. My suggestion is that you could go back and insert that 17 rather than retyping it, and we get out a smaller number, 1.6368. As time is going on, the dye is getting diluted. It's getting pumped further from the heart. Okay, so what does this mean? In 4 seconds, there is a dye concentration So in 4 seconds, there is a dye concentration of 3.8393 milligrams per liter. In 17 seconds, there is a dye concentration of 1.6368 milligrams per liter. And so we can see as time goes on, the dilution is decreasing, and that is again why this test would be over after so many seconds. So these problems look complex. There was a lot of information, but it really is just plugging in the value for time and getting the output. So if you take the time to read the beginning of the problem and understand that f of t stands for the dye dilution and t stands for the time, we're plugging it again right into that equation, and then knowing what we have is different than knowing what we would do with it in the medical profession. And so there is someone who is reading this and giving the results to their patients, and again making a decision whether there is a medication needed or a surgery to help them if they're having problems.